Okay. Well, it's great to be back in ICAM again, and what I'm going to do today is give an overview of some of my thoughts on the development of advanced materials, and I'll brush on the role of Royce in helping to develop both new materials and to better understand the materials we have around us, and also to look at ICAM and its implications for ICAM. So, I think I've shown this slide a number of times before, but it is it is not surprising really that we define our ages by the materials, because what we can achieve is largely defined by the materials we have to hand. If we have only stone to build with, we are going to struggle to make aeroplanes. If we have no polymers, we would struggle to make good seals, for example. So the materials we have to hand shape the world that there is around us, and of course our aim is to develop new materials and new capabilities to expand our horizons. I'm just going to show a slide I've shown a few times before. On the left-hand side, it goes from weak to strong, and along the bottom, from lighter to denser. So good aerospace materials, for example, are in the top left. Good paperweights, perhaps in the bottom right. Clearly, many years ago, natural materials were all we had, along with gold and as a metal. But over time, those materials have increased, and if you look here, we have concrete. So the Romans brought us concrete or cement, and that massively extended what we could do in terms of civil engineering. Wrought iron, cast iron, new materials, more metals, lead, again extended our envelope. Through rubber, the invention of natural rubber was a massive, or finding of natural rubber was a massive breakthrough in terms of a whole range of applications. Polymers, the epoxies, bakelites, and then the vast array of polymers we now have today. And of course, composite materials are now seeing really heavy use across the world. So new materials have always been important. They define our success and they define our horizons. And again, I thought it was helpful to look at how materials have developed over the last 100 years. And of course, originally, 100 years ago, it was predominantly a direct one-to-one replacement. So plastic for leather, PVC instead of lead and copper, aluminium in beer cans and so forth. So one-to-one, like-to-like replacements. Then new materials came out with increased functionality and magnetic properties, electrical properties, and so forth. But more recently, there's been a move towards what I would call material systems. Even if you think about graphene, and graphene, of course, is probably one of the few new materials we've had in recent years. Even graphene, it's not so much graphene as a material, it's graphene as a device or a system. How do you incorporate graphene into products? How do you make things with it? How do you design things? How do you incorporate it and add functionality? And I think material systems is where much of the value arises. And of course, if you want to make material systems, you often need to have a very joined up materials development, supply and development chain. I took this from a report by Deloitte, and what it shows is really the value add of new materials. What's the return on net assets? And if you look at materials per se, the value add for materials per se is less than the value add for new material systems. So again, I think Royce is going to be looking towards the development of systems. That might be a new alloy with a specially designed substrate, with a specially designed coating to give a combination of properties. And it's only when you bring those two together that you get the properties that you're after. It might be a device where you have a series of components brought together to make a system. Another change over the last 200 years is the way we make things. So originally, of course, Manchester was very much caught up in the first industrial revolution. My own village has a number of large mills and a number of large ponds that were used to power those mills. and many people made, many people eked a living, and a few people made a lot of money out of the first industrial revolution. As we've moved on, so the second industrial revolution was about mass production and assembly lines, and then through to automated assembly lines. But today, the big opportunity is through a more integrated and more interconnected supply and delivery chain, with the use of sensors and the use of electronics and computing to control and optimize processing and to ensure optimal properties. So there's a very good review called Made Smarter that was written in 2017, and that talks about 100 trillion worldwide benefit from what is called digitalization and massive increases in productivity. Of course, automation and connectivity coupled with real-time processing and re-engineering can lead to efficiencies, it can lead to optimization, and it can lead to better products. Equally, new manufacturing technologies like additive manufacture place a greater emphasis on our ability to design and control the process. It gives us the ability to lay down materials with gradient properties, gradient microstructures, and gradient compositions. New industries are starting to arrive in terms of the control of your system. I mean, you only have to look at the home now. You can buy software that you can place in your home to control the heating, lighting, what you're watching on television, what you've forgotten to record, or to put the dinner in the oven, or at least to turn the oven on if you've forgotten to do that. So there's a whole range of environments that now are controlled and can be intelligently monitored through an interconnected system. At the same time as connecting with the real world, there's also the opportunity to create a digital world, the digital world of that part, so something called the digital twin. So in addition to making a real component or having a real asset, a real pipeline or a real plant, you can also have a digital copy of that. And you can follow that digital copy right the way through its manufacturing or right through its life, so that you monitor its performance, you monitor the environment, its experiences, and clearly that's been done for some time in some ways. I mean, for example, if you fly, every flight is recorded, the engine history is recorded, and at a certain point in time, the engine manufacturer will call that engine in for a service, and it will be based around its traditional operating cycle, but also in terms of the number of high power surges that engine has undergone because of a false landing or because of turbulence or because of some emergencies. So you monitor the whole life and you take that whole life into account. It enables you through that to get the best value from your asset, and hopefully it helps you to take components or assets out of service before they will fail. But not so early that you lose competitive advantage. And clearly, in the nuclear industry and in the oil and gas industry, you have plant that is very inaccessible. You may, in the nuclear industry in particular, you have plant that is difficult to monitor, incredibly difficult to repair and replace. And so, if we can understand the lifetime and its influence, the influence of the environment on lifetime, then we can optimize and prolongate the life of components and systems. Of course, that digital thread shouldn't just exist through life, it also can exist through manufacturing. So that if you've got a supply chain where a part is perhaps a raw billet is forged, that billet is forged, heat treated, then it's machined, it may then be heat treated again, it may be peened, it may then be coated, it may then be welded, it may be added to other components and put together. You can follow that whole manufacturing process through a digital thread. And what that enables you to do is to optimize the process. or at the current time, for example, if you were to take Rolls-Royce, they have certain specifications to each supplier in the supply chain, and those specifications are not joined up in an integrated way. And so you may be paying to reach a certain specification in one part of the process, when actually a later part of that process means that you do not need that level of specification. In other words, you may be adding price. Or you may be failing to pull out parts early in the process that will lead to non-conformance late in the manufacturing process, which again leads to unnecessary waste. So a digital copy, a copy that runs through the manufacturing process, and whereby the process is monitored electronically through sensors and through process parameters, enables you to understand the precise manufacturing of each part, and also to correlate the best performing parts with the best optimized process. So you can learn how to make better. So that requires quite an infrastructure in order to put together all the parts of that digital thread. And indeed, many companies already have significant parts of that patchwork digitally enabled, but there are very few companies, I would argue, that can do that from conception of a part right through to its final delivery. Another topic that's really important, I think, in terms of new manufacturing opportunities is machine learning. So once you've got all that digital data about your process, can you use machine learning to learn how to make that part more reliably, to learn how to make them? When I was a kid, I was brought up at the time of great British quality cars like Chrysler and Allegros and so forth. And we used to talk about Friday afternoon cars. I don't know whether we still have Friday afternoon cars, but what you really want is Monday morning style cars, you know, when people come in and make the best car they can make. So can we learn what leads to a Monday morning car or a Monday morning component and avoid Friday afternoon components? Can we optimize the process and understand what tolerances are really important and what tolerances are not? And the other aspect of this digital revolution is that we need to understand materials better. We need to have better data on materials. And traditionally, a material scientist might know the grain size, they might know the composition within a certain specification. But if we understand the material better, we may find by simply tightening a specification, we can lead to better corrosion resistance, or by just tweaking so that we always take a material at one end of a specification, we may get a better set of properties. But do we at the moment have the knowledge to store all that information? Do we keep a digital fingerprint of that material so that we can make those connections and we can use current knowledge to make future designs? So materials informatics is a relatively new topic, but I think an increasingly important one. So if we're looking at designing materials using computing, there are two really, I think, significant approaches. There's one is a kind of physics-based approach where you basically model the material at different length scales from basic physical understanding with some empirical filling in where necessary, or do you take a learning-based approach where you don't strive to understand at a basic physics level the process, you simply learn to understand what aspects of the process lead to good properties and which ones to bad. In general, you're likely to take some kind of hybrid to materials discovery which combines physics-based models where appropriate with kind of learning-based models. And I'm going to take just a couple of quick examples of that. So just here's a kind of picture of that whole process. Originally, you know, experimental design, then the use of basic thermodynamics, and I remember being taught Ellingham diagrams, and how simple laws can be used to predict certain outcomes. Then more detailed sort of atom-up type modeling, and now big data-driven science. And we really need to understand all of these approaches. None of them are redundant. They all have benefits, and they all need to be woven into our materials palette, if you like. So if we look at materials physics approaches, I think there clearly is massive advances in terms of quantum mechanics, the ability to predict atom-to-atom interactions. But it isn't possible to build large-scale structures, nuclear power plants, aircraft, based purely on quantum mechanics, much as many of us would like to be able to do so. What you need is different models at different length scales. And then the key point is, how do you bridge those length scales? So how do you connect models at different length scales together? And how do you exploit that? So one of the big challenges at the moment is not just the development of models at these different length scales, from finite elements at one end to these atomistic models at the other, but how do we put them together, and how do we make sure that the connections between those different length scales are correct, and we're carrying forward the right parts of the previous model, the right inputs for the next length scale. The second approach, as I said, is machine learning, which is really to use the power of supercomputers. And I've taken this little example here. This is in the chemistry area, and it tends to be in the chemical formulation area that a lot of machine learning is taken off. It's also used heavily in the drug formulation and bio area. And interestingly, material scientists say you can't use machine learning because material science is too complicated. Whereas biologists say you use machine learning because it is so complicated. So I think it's an interesting, we all pick the models we're comfortable with, perhaps. But in formulations, it's certainly possible to go through many billions of molecules to look at different conformations and different compositions to build up, literally an infinite variation of molecules. It's estimated here 10 to the 60. But then, of course, once you've got those structures, you need to work out which ones are promising and which ones are likely to be stable and so forth, and you can limit that down. And then you can start to use machine learning to try and refine the number of tools down to the thousands. And then you can start to use robotics and automation to go through a whole series. And for example, the Royce is doing quite a lot of work at Liverpool, and they have an automated system where they can make many molecules very quickly. And then, of course, you've got to evaluate those molecules. I shouldn't say 103 molecules, of course. I should say 10 to the 3 molecules, but never mind. But of course, all these machine learning methods are very data hungry, and we do need to think about how do we store data. I mean, I was at a talk in the US a couple of years ago, and they were developing programs to read science papers to extract chemistry recipes. If you think about it, if you make a cake, you get a recipe at the front and it tells you how to make the cake. There isn't a standard format. You can't put it in a computer and out pops a cake, or into a kitchen with a piece of punched card. Put that piece of punched card into your kitchen and out comes a cake. But if you think about chemistry, if you read chemistry papers, the way they describe their manufacturing is totally different, and there's no simple way of recording that. So they were writing computer software that would read chemistry articles to extract out the recipes, so that they could learn that if they wanted to make one molecule like this, maybe someone has made one similarly and they've made it in this way. Because it's not simply the thermodynamic stability of those molecules, it's the makeability. How do you make those molecules that's important? But our formats for storing data, materials data, are not really appropriate for a machine learning, data-hungry environment. As a metallurgist, we don't do that in terms of microstructures, and I'll come back to that in a moment. I mean, a company like Rolls-Royce might collect 100,000 micrographs, 100,000 pictures every year. And I asked them, how many do you store digitally? And they said none. In other words, they do store some of them digitally in the form of reports, so a few images in reports to satisfy their conclusions, but there is no structure. There is no fingerprinting database. There is no genomic store with all those digital combinations stored. And so we need to think about that. If we want to move into a more data-intensive paradigm, how do we store data? How do we collect data and make it suitable, not just for human beings, but for computers to take advantage of? So I've just been thinking a little bit through Royce about how do we do these things, and of course databases are really important. How do we collect databases? All this government money is going into research, and we all promise to make data available, but just like those recipes, we don't make the data available in a way that that data can easily be exploited. And so we also need to think about this, not just in terms of the data, but also in terms of the experimental tools that we use to collect that data, so that we can create a kind of virtuous circle which allows us to design materials, to go away and make them through experiment, and to test them not at the 2-ton billet length scale or weight scale, but to make them in small quantities in ways that are reliable and can be extrapolated to large quantities, but allow us to evaluate quickly and in a flexible way. So where is the Royce in all of this? And I'll give you some insights into the Royce and how I see things moving forward. So the Royce Institute is at the moment is a £235 million amount of funding to build an institute in Manchester connected with partners in Cambridge, Sheffield, Leeds, Liverpool, Imperial, Oxford, National Nuclear Labs and Culham. It sits working alongside universities, or a bit like ICAM in the sense it sits working with universities and industry and other organisations. And its aim is not to be a closed shop, but an open environment. As I said, the hub, those of you who walk down my end of Manchester can see that they've started to build the hub, and the hub will be not just a place where some of the research is done. I hope it will truly be a national or international meeting place where we will come together. I think ICAM is an international meeting place for BP. It's been fantastic in my time as director how many BP people came through the threshold. If we could do that for 20 large companies and 100 small companies, multiplying what has been achieved with ICAM across that scale, it would be truly magnificent. Okay, so in many ways, much of what we're doing through the Royce is learned from lessons I've picked up through being involved with ICAM, and I hope we can have some of the impacts and get moving quite as quickly as ICAM has managed to do. The 4 areas that we're supporting: digital, engineering materials, energy materials, and health. And the work is split into 9 areas within those themes. And the reason that we've done it this way is because this is a partnership with 6 other universities, and it's really important that each university takes some responsibility to lead and to nurture materials across the UK, not just in their own institution. So if you take energy storage, for example, Oxford are leading that, but they're also working with the Faraday Institute to create a significant driver for change in energy storage, working with universities like Warwick and Cambridge, Manchester, elsewhere. So it's being champion is not being, it's not like being the gatekeeper. It's more about opening the doors and trying to make sure that we can work across the UK, and that we have the right equipment, and that equipment is made available both to academia and to industry. So Oxford, energy storage; Sheffield is leading on advanced metals processing; Liverpool on chemical materials design, and many of the ideas I'm talking about today are very much part of their formulation and invention strategy; nuclear materials in Manchester with NNL and CCFE; and materials for energy efficient ICT at Cambridge; atoms to devices at Imperial and Leeds; materials for demanding environments, which is very important in terms of the work we've been doing here in ICAM at Manchester; biomedical systems and devices at Manchester; and 2D graphene and other related materials at Manchester. But of course they all join up. And this is a diagram. I think Tracy Annis calls this my lava lamp, but I've shown it here, which just shows the balance between transformational, really exciting, way out there kind of research, through to applied research, through to today's problems. And just as I think we've worked hard to try and make ICAM deliver in these 3 areas, I'm trying to make sure that Royce can do the same, that we can be on hand to provide the facilities to help answer questions, the unknown unknowns, the things that come up very quickly that you need to draw down solutions on the daily or weekly or monthly type timescale. That's at one end, and that's largely industry funded, right through to projects that are largely government funded. But there are also those applied research areas, and I'll come on to one, the Prosperity Partnership with BP, which is a really good example of combined government and industry research for applied research. Again, if I think about how we're trying to put Royce together, this is often shown as the kind of model in Britain for how innovation leads to new commercial products. I think it's a very neat way of showing it. It shows technology readiness levels that move from 1 to 9. And of course the idea is that you get a concept in a lab, and that then moves into some kind of demonstrator product, and it gets seed funding and venture capital funding and then industry funding, and eventually becomes a product. And that would be really nice if it was just like that. But my view is that it's somewhat more complicated. And I show this picture, which is my picture of the innovation landscape. It's really about snakes and ladders. So you move up this, as you move up this board, you move from TRL level 1 to TRL level 9, you very often land on a snake because you don't know what you don't know. So as you scale up, as you move the thing through the product development chain, there are things that you haven't considered. And those things require a really basic science understanding. So you have to go back down to understand the basic level before you can climb that ladder and go back up to the TRL levels. So I think the idea in the UK that we can have universities and then catapults and so forth all in this linear line is not the right way to do things. What we have to do is we have to make sure that things can go backwards and forwards so that companies can access very basic research very quickly, so that we can work with the catapult, so as they develop a process they can get scientific background from us and so forth, because it really needs to be a much more active environment. The other point is that the UK until recently had always funded what I call boffins, and I mean that in a nice way, but basically they had a beauty competition and they gave all their money out to the best and the most beautiful bids. But what they never did was think about, well, how does that join up? So they never thought, so if they put an MBE into Cambridge, or they put a tribology set into Southampton, for example, they never thought about, well, how does this all build together? Whereas recently, there's been a lot more funding, which is challenge-led. So instead of putting the funding into lots of areas and hoping that it will flower, you say, I've got a challenge. I mean, the obvious challenge is I want to go to the moon. If you want to go to the moon, there are certain things you have to do to get to the moon. You need to have a rocket, and you need to have the right fuel, and you need to have the right navigation systems and so forth. And you have to put all of those pieces together, because if you don't get them all together, you don't get to the moon. If you could have the world's best heat-resistant materials, and you can have the world's best spacesuits, but if you don't have the rocket fuel, you don't get to the moon. So challenge-led type science is much more joined up. You have to join the pieces up. And of course, what I'm trying to do with Royce is to join up the facilities and say, well, okay, can we move between different labs? Can we move between different facilities to try and exploit this to satisfy certain challenges? Of course, the advantage with challenge-led type funding is that you still need those boffins, you still need that expertise, but suddenly they're working as part of a bigger landscape. So within Royce, what we've tried to do, or we're trying to do, is to build landscapes for different areas. So this is an advanced metals processing landscape, and it includes computation, it includes make, it includes fabricate, it includes evaluate, and it includes what I call products. Now these aren't really products, they're research products. They're not things you go and sell in the high street, but they could be, for example, a new lightweight alloy made by some modern casting method with an appropriate coating on to give it salt resistance or whatever. But the point is that what we're trying to do is build up these kind of ecosystems, and we shall see whether we can actually drive research through them. And that will be an interesting challenge, but this is the aim. Here's another one. This is materials for demanding environments, and they're looking at coatings, high pressure and high temperature environments. They're looking at sweet and sour resist degradation. They're looking at in situ testing. They're looking at hybrid materials. So you can see in different areas, these kind of landscapes and these kind of facilities will be different. Some of them will be specific to one application. So, for example, the hydrogen sulfide type testing might be specific to the materials for demanding environments. But the coatings development might be useful to biomedical as well as nuclear, as well as engineering. So it's a mixed and complicated landscape. But the idea is that you're trying to put the equipment together. The other point comes right back to what I said earlier about materials design. Can we create small-scale testing, automation, and high throughput characterization so that we can quickly evaluate which of those guesses are the right guesses, or at least in the promising directions, and which guesses are going to be unproductive. And we need to move away from having 100-ton billets. We need to move to small samples and fast and flexible methods. In fact, Alan and I were meeting a coating company yesterday, and they've got 6 candidates for a replacement, and they're thinking about how do we evaluate those 6 coatings, those 6 potential coatings, when they've got to last for 10 years on a surface. How do we evaluate those, and how do we quickly work out which are the better ones? But wouldn't it be fantastic if instead of 6, they were actually considering thousands computationally and hundreds experimentally? That would lead to a much more exciting and transformational materials delivery chain. So, as I said, you need to be able to feed machine learning with data. You need to data is absolutely critical. You can't use these kind of computational processes. You can't learn quickly if you have no data. So this is another little project that I think is really critical, and I'm trying to get a relatively small project started, but it's what I call the digital microstructure project. You remember back I said that Rolls-Royce collect hundreds of thousands of images, but they have no way of storing them. It would be just like the police collecting fingerprints around the world and say, well, I've collected this fingerprint and I need to compare it with everyone else's. And they went round and tried to compare with hundreds of thousands of fingerprints all around the world. What you need is a characterization of that fingerprint so that you can say, well, there are a number of parameters that characterize that fingerprint so you can compare it digitally with all the other ones. And you need to take essence of a fingerprint, if you like. So what is essence of microstructure? So here's a microstructure, for example, and this is just one approach. This was suggested by Liz Holm from the States. But here you can see there are some different phases. There are large phases and small phases. You can see different grains if you look carefully. But what you want to do is to extract features. In the same way that you don't have a box of you don't, when you recognize faces, you don't have a number. I don't recognize Alan because he's number 43 and Julia because she's number 62. There are elements of Alan in common with Alex because Alan has glasses and Alex has glasses, but I don't always get them confused. I sometimes get them confused. But there are features and aspects that you store which allows you to make those characterizations. And can we develop ways with dictionaries where we can characterize structures and say, well, this particular microstructure has a certain characteristic, and can we therefore put that into a computer in the same way that a fingerprint is recorded? And you can see that there are thousands or hundreds and thousands of microstructures, but wouldn't that be great? Because it means that when a supplier supplies you with a batch, you could actually take that batch and you could compare that batch with the previous batch and say, well, actually, it's different from the batch you gave me last week. And they may say, well, that's because we've got a new furnace or a new rolling mill or whatever. Now, that may be absolutely critical to you, and especially if you realize it 2 years later that the first batch lasted longer than the second batch. Suddenly you can start to you can start to control microstructure. So I'm suggesting that digital fingerprinting of microstructures is a breakthrough we need to have quite soon. And of course, I'm a characterizer, so I look at things, and we talked about an eye on materials. This is a fantastic picture from 1665, one of the very first microscope images. There's a wonderful image of the flea from Robert Hooke, but this one of the fly. And we have improved, we have moved forward over the last few hundred years, such that now we have tools that are unparalleled in terms of the resolution and capability. So instead of just looking in 2D, now of course we can look in 3D. I hope this will run. It might, yes it will run. So we now have a machinery to collect lots of information. I'm suggesting we need to put in place the frameworks that we can characterize those things we see in a more digital manner, so that we can so that our characterization of images can move on to keep up with our characterization, our instruments. Our instruments have improved, but our ability to characterize microstructure has changed very little in the last 100 years. And of course we have many techniques. So we have non-destructive 3D techniques. We have destructive 3D techniques. We have methods of cutting up and manipulating samples so that we can find the bits we want. We have analytical modalities, so we can pick up the chemistries, we can pick up the crystallographies, we can relate that to the properties, the local properties of that precipitate, or the local properties of that part of the structure. So we can now collect masses and masses of data, and we need to think about how do we use that data to understand better the materials we have and to move forward to design new materials. And this of course was a project we did about 3 or 4 years ago now, and it was Ellen from BP charged us with going to do a project to show what we could do in ICAM. And in 2 weeks we covered 9 orders of magnitude. So this corrosion we could study at the large scale with electrochemical methods, then at the millimeter and micron scale with X-ray tomography, and then at the submicron and nanoscale by using electron imaging. So only by building up a picture across many scales could we really understand that corrosion product. And indeed, each scale gives us a different opportunity. At the large scale, we can understand we might coat it with a paint, or we might coat it in some way. At the grain scale, we may change the grain textures, or we may change the composition slightly. And then at the grain boundary scale, we might change the atoms that go to that grain boundary, which can prohibit corrosion. So at the atomic scale, at the grain scale, and at the meso or coating scale, we can affect what goes on, but only if we have the tools to see across those levels. So within Royce, one of my aims is to make sure that we have a world-class infrastructure to characterize. And the challenge to Royce is, can we make that available to companies, both large and small, for both long-term and short-term research. So I think that's an opportunity for BP, and we have to make sure that those facilities can deliver new insights. Okay, so I hope that gives you a bit of an example of one way in which the wealth of facilities, both in Manchester and across the UK, can be threaded together to try and answer some fairly fundamental questions with some very applied consequences. I think ICAM is a model for how to do international collaboration, and a model for Centres for Advanced Materials. I hope we've learned some of the best lessons from setting up ICAM in setting up the Royce Institute, and I really look forward to Royce and ICAM working together with companies like BP to deliver new materials and to better understand the ones we have. Thank you very much.